So now we're going to discuss Landauer's principle. And the main idea of Landauer's principle is that information is physical and has physical attributes. This has some interesting implications. Firstly, that if you try and erase information, it actually takes energy. So, let's consider a sheep as our bit of information, and to erase this bit of information, you need to shear the sheep. So you come at it with a razor, and what you get is a sheared sheep or an erased bit of information. And as I said before, it takes energy, and the energy is equal to the Boltzmann constant times the temperature times the ln of 2. This is known as Landauer's limit. Another interesting implication is that erasing information also increases the entropy of the system. So if we imagine our system to be a flock of sheep in a pen, all nice and orderly, chewing grass and whatnot, and you come at this pen of sheep with a razor, and of course that's going to freak them out because who wants to get shaved? You're going to increase the disorder of the system, and sheep are going to be everywhere, and it's going to be a lot harder to shear the sheep. So if the sheep is order and the razor is the erasure, then we increase the disorder. And this increase in entropy is equal to the Boltzmann constant times the ln of 2. And this is known as Landauer's bound. Now, this has some applications for solving of Maxwell's demon, which we discussed earlier. So, the key is to consider the demon's mind as a physical system, where physical information is placed and needs to be erased. So initially, he has some information about where the particle is, and eventually he will have new information as to where the particle is. So if we give the initial information a value of 1, and then conduct a cycle of Szilard's engine, we need to erase the initial information and introduce new information. Now this erasure, of course, takes work, because it takes energy to erase information. And the work it takes to erase information is equal to the negative Boltzmann constant times the temperature times ln of 2. But, as we know from before, the work that we get out of Szilard's engine is equal to the positive Boltzmann constant times the temperature times the ln of 2. This means that if you treat information as physical and conduct Szilard's thought experiment, you find that the work it takes to erase information is equal to the work you gain from the engine, and therefore the second law is saved.
The fluctuation theory. The fluctuation theory is a way to prove the second law of thermodynamics. A consequence of the second law of thermodynamics is that the entropy tends to increase as time goes on. What the fluctuation theory states is that this is not strictly true, only statistically true. This means that for thermal and statistical physics, which deals with large systems of uncountable numbers of particles, entropy increases. But on a small scale, entropy may increase or it may decrease, but it is simply much more probable that the entropy will increase. The probability of the entropy increasing is given by the equation. The probability that the sum of all of the entropies is equal to A divided by the probability that the sum of all of the entropies is equal to negative A is equal to e to the power of A times T. Given that both A and T are positive, the lowest possible value of this ratio, the value where A is equal to 0 or T is equal to 0, is 1. Given that if A is equal to 0, then both A and negative A are the same, this solution is trivial, the ratio is always 1. For all A greater than 0, as the time gets larger, so does the chances that the entropy will increase. Also, as the values of A gets larger, the chances of the entropy being positive compared to the entropy being negative increase. By the time you consider huge macroscopic systems with trillions of interactions, this is less of a probable statement and more of an absolute certainty. This means that the average value of S is greater than 0, and for large systems, this means that delta S is greater or equal to 0. There are many applications of this. A noticeable application occurs, unsurprisingly, in a very small system. One of these such small systems are the molecular machines that are inside of the mitochondria. Because these machines are so small and contain so few interactions, entropy inside can sometimes be seen to spontaneously decrease. This makes the machine take in work from the surrounding area and run in reverse. This would be like in a gas engine if the gas unexploded, creating gas, but the wheels kept on turning. In large macroscopic systems, this is impossible, but in tiny systems like the ones in the mitochondria, this is possible. From this presentation, we have learned that information can be expressed as entropy, that the possession of info has thermodynamic implications, that information is physical, and that entropy can decrease. Thanks for watching, and don't forget to like and subscribe.